Okay, we will continue with the other mode of delay modeling, which is called transport delay. This is intended for a slightly different purpose from gate delay, the delays due to propagation delays due to transistors, but this kind of delay is useful in modeling delays through wires or transmission lines, or in general when there is an abstract model of a component that could be simple or complex, but there is a certain amount of delay that we associate with that component. The difference here being that the spikes are correctly propagated. The essence of the inertial delay was that if the input is changing too fast, considering what the propagation delay is, then the spikes are hidden, they are absorbed, you do not see the spikes in the output. But in transport delay those spikes are visible. So, this is an example, you have y takes the value of transport. So, that is the keyword that is used, and the functionality is not A after a delay 10 nanosecond, but the presence of the transport keyword makes this difference. So, if the input goes from 0 to 1 here, then the output changes after 10. The input here changes from 1 to 0 and the output changes after 10, this is fine. But in the other case where you have the input changing from 1 from 0 to 1, that leads to an output change for 10 nanoseconds later, but the input changed too fast, right, input has changed before the propagation delay. Transport delay will still go ahead and schedule the next event for 10 nanoseconds from the time that the input changed. Okay. So, that is one fundamental difference between these two delay models. Which one to use depends on what is the kind of modeling that you really want to do. Normally, if it is CMOS gates that we would like to model the delay of, then we would use inertial delay. But if it is something more abstract, little higher level of modeling, then we could use transport delay. It could also be that you have long buffered wires or something like that, then to transport delay could be used for modeling. Okay. So, these are the two modes. With that much background about how the delay is modeled, it is worth taking a look at the internals of an HDL simulator and understand a little bit from the simulator's point of view what is happening when we assign values, when we change values on signals and ports and so on. So, as we do our modeling, we need to have an understanding of how it will be interpreted by the simulator, of course. So, two things, one is an event occurring, other is a transaction being posted or scheduled within the simulator's framework. Event is said to have occurred if we have a signal assignment that causes a change in the value of that signal. Okay. So, it does not matter what the type of the signal is, if the value is changing at a particular time, then we say that an event has occurred at that time. Transaction refers to a value being scheduled for signal assignment. This is internal to the simulator, not necessarily visible to us as the user or even as we observe the waveform of the simulation. It is not immediately obvious, we have to do something to take a look at what this means. Also, what is the difference, let us try to understand. A value is scheduled for signal assignment, it may or may not cause a change in the value of the signal itself. When that happens, let us just take a look, but these are the two elementary concepts that are used for delay modeling. Let us understand the difference, the way this works, and finally how it translates to interpreting inertial delay and transport delay in an HDL simulator using a simple example like this. I did not show the entity here, but it is not very important. A, B, C are three signals that we have in this design, and these are initialized to 0, and I have three assignment statements. A takes the value of 1 after 15 nanoseconds. what kind of waveform does that result for A? So, you have time 0, this is time. For signal A, you just have, so remember it is initialized to 0. So, what waveform are we talking about here when I say A takes the value of 1 after 15 nanoseconds? So, if this is 15, then it stays what it was, it stays 0 for 15, but it takes the value of 1 out. Later on, what happens? It stays that way, there is nothing else that happens. So, for the rest of the simulation time, that is the waveform for A. B takes the value of not A after 5 nanoseconds. That also should be obvious, one can infer it from the waveform for A itself, and then I have C takes the value of A after 10 nanoseconds. That is all that is there in the design. Let us just trace through the simulator's waveform, but also in the process understand these differences, first of all between events and transactions, and then later on between inertial and transport delays through this example. Here is my waveform. I have all the values being initialized to 0 at time 0. Okay. So, A, as we saw, takes the value of 1. So, there is a transition at time equals 15 nanoseconds from 0 to 1 for A. But let us just understand it from the simulator's point of view. We are assigning a value of 0 at time 0. That too is a new value, that too is a change in the value, because there was no value before time 0. Since simulation started at time 0, new transactions are scheduled for each of those signal. So, it means that at time 0 all of these statements are executed. This is consistent with the overall semantics. When will that signal assignment be triggered? We said that it will be triggered if anything changes on the RHS of that assignment statement. But of course, at time 0, this is a special case. If there is a variable or if there is a signal on the right hand side, that value did change at time 0, because there was nothing before, and at time 0 there was some initialization. So, that is a change in value that should trigger the statements, not merely those statements in which some signal is there on the RHS, but also other statements like this, which are actually not sensitive to any signal, but still all the signal assignments are executed once at time 0. So, that just to start off the simulation. Executed is interpreted as what actually happens when we say signal assignment is triggered. Here is what happens: transactions are scheduled in the simulator for all the 3 signals ABC. This notation here is just saying that a value of 1 is scheduled for a time 15 nanoseconds from wherever we are now. Okay. So, that 15 there is a relative time, it is the same as when we say 15 here, what we mean, it is 15 from wherever that execution is happening, wherever that statement is getting triggered. Okay. So, such a transaction A115 is what is now stored in simulators. A bunch of transactions are scheduled, they are stored in the internal queue of a simulator, and so this is one of them. A115 is one transaction. B15 is a transaction corresponding to that statement being executed at time 0. Does that make sense? A value of 1 being scheduled on to B after 5 nanoseconds based on what that statement is. Why is the value 1 being scheduled?
Because A is 0.
Currently A is 0, right. The new value has not yet appeared, of course, on A. So, it takes the current value whatever is there. That current value is, remember, is a new value, because at time 0 everything is new. Not of 0 is 1. So, 1 is scheduled on to B after 5 nanoseconds. Fine. C takes the value of A after 10, that results in that transaction 0 10. Current value of A is 0 and it is being scheduled after 10. So, these are the 3 transactions that are entered into the system at time 0. So, when time changes, maybe some new events occur, then we will subtract some transactions from there, remove some transactions and add possibly new transaction. That is how the simulations working goes. Yeah.
Time 59 event is created because A is changing from 0 to 1.
events are created on ABC just by default because this is time 0. Okay. So, as of now we have only talked about transactions being scheduled, event has not been created other than just those default events of everything being 0. Okay. So, since I have 3 transactions here, A being 1 at 15, B being 1 at 5, C being 0 at 10, we just proceed from here, we forward the time. This is an event driven simulator. The way the simulator works is it keeps track of all the transactions currently that have been scheduled into the future, okay, and picks up for processing which one? The one that is scheduled for the earliest. It works in a way that is intuitive, but it is an important mechanism for simulation. Specifically what it means is, this is 5 nanosecond, right. It seems as though out of our 3 transactions that are scheduled, we should be picking up this one for processing next. But as a consequence of that, you see what we are not doing is we are not evaluating the state of the system at all these intermediate steps. Right. Conceptually, this is what event driven simulation is about, which is we do not divide time into fine grained intervals and trigger the simulator at every time unit, right, whether it is every nanosecond or picosecond or femtosecond. We do not do that. We automatically forward the time to whatever is the next interesting event and thereby retain all the old values for that duration. You could do that because this is a digital simulation. All types of simulations do not work in this mode, but this kind of a simulation where you can forward time and the assumption is that all the values are retained during that entire period is an important part of the event driven simulation semantic. Why do we do it this way? Of course, this is an efficiency issue from the simulator's point of view. If it had done all the intermediate evaluations, would it have made a difference? It would have made a difference to the processing time, it would not make a difference to the waveform. You would get the same values. In fact, there is nothing that is happening in that system in that intermediate stage. Of course, this is set up in a way that it is okay to move forward in time. So, if it was not nanoseconds, but these values were seconds, would the simulation be faster or slower? No difference, because the simulators working, the speed of the simulators working is a function of what? Is a function of what transactions we are putting into the event queue. That is what would be called an event queue, and you pick up transactions from the event queue and process them. That is only dependent on the frequency at which those events are getting in and getting out of that event queue. In fact, it would make no difference if all those units were seconds or years or something like that. Conceptually, it is the same thing that is happening. Then we pick up that transaction B15 and process it. Yeah.
Pick up that particular B15 operation.
Yes.
We need to know the present state of A. Only then we can not say.
To pick up the B15 operation, do we need to know the present value of A?
B is nothing but not of A.
Right. So, but to pick it up, do we need to? No? No. Why? Actually, that value we have already entered here, right. So, the current value of A, you mean that the current value of A at 5 nanosecond is actually not relevant to this simulation. What the value that is relevant is the value that we evaluated for B at the time that the transaction was created. Okay, so that is being scheduled. So, 1 is being scheduled. Where did that 1 come from? It came from not A. We took the value of A at time 0. That is the transaction that has been scheduled. So, here it is only the values that we are putting there. We are not putting what function is it of other signals. That function was actually computed when we evaluated the signal at time 0. That is how the simulation proceeds. So, we do not need to look at the current value of A. Not that it should not matter electrically, and when it does matter, let us see what we need to do about it. But in fact, the fact that there was no other transaction, no other event and so on between 0 and 5 gives us the guarantee that it is okay to pick up that old value of A. A's value has not changed since that time. That is what we are guaranteed, therefore, we are able to make that assumption. Okay. So, when we pick this up for processing, we say that the transaction expires. So, this what is maintained here is an event queue, and what we picked up from there is the first element, the earliest element that is scheduled in the event queue. So, after I take that away, what would remain in the event queue are the other two transactions A and C. The B15 transaction is taken out. Yeah.
Sir, if the value of A would have changed, say, at 2.5 seconds,
Right.
2.5 nanosecond,
Right.
then would B have been, would the value of B have been evaluated?
If the value of A had changed in the middle somewhere at 2 nanoseconds, then would this transaction still be evaluated in this way? In fact, what does intuition tells us? No, but we did not see that happening here. Here actually we are guaranteed, right, that it would not happen. The reason we skipped 2.5 nanosecond was that the transactions were scheduled in a way that such an event could not have occurred. But when it does occur, we do need to do something about it. But in fact, our specification of inertial delay was that we would be sensitive to such things happening, right. The spikes should be suppressed, that is what we had said. So, we should be able to do that, but how we do that, let us just proceed along the waveform, we will see an example of that happening. So far this is not happening, and all we do is we remove that B15 transaction, and that is it in the event queue so far. After that, I have two transactions still remaining to be processed. So, I just pick up whatever is the earliest transaction, which is that C010, because the 10 is earlier than 15, and therefore, that is the transaction that is picked up. Okay, the one thing I forgot to mention is that when the transaction is expiring, because we picked it up, we now posted the new value as scheduled in that transaction onto the signal. Now, if as a result the value of the signal is changing, then we say that an event has been created. Okay, so, this resulted in an event being created on B. Let us move to the next transaction. I have a 0 value being scheduled onto C at time 10. I pick it up because that is the earlier signal anyway, earlier transaction to be scheduled. I post the transaction. What happens to the value of C? There is no change, because the current value is 0 anyway. This is an example of a transaction that is scheduled, that is processed because it expired, its time has come, but it did not result in the creation of an event, right, because the value of C did not change, it did not result in C changing. As a result, if there was some other signal that was sensitive to C, right, it had C on the right hand side of the assignment, then that signal assignment would not be triggered. Event driven simulation means that you trigger signal assignments only when the appropriate condition has been met. But here it is okay. So, transaction expires, no event is created because nothing changes in the value of C. Move on. This is the last transaction that is still there in the queue, right. It was scheduled for 15, the value of A was supposed to be 1, and so that is what has happened here, and as a result an event is created on A, because the current value of A is 0, the value of A has changed to 1. Let us see what happens later on. Because A has changed, now some new transactions may be created, right. The simulator has to look out for the possibility of new transactions being created, resulting in new statements being executed whenever any event takes place. So, now that an event has occurred on A, what might happen in the other two statements? In fact, both of these statements have A on the right hand side of the assignment statement, right. So, they are candidates. So, new transactions may need to be scheduled for both of them. So, we will evaluate B. A value of 0 is scheduled for B for 5. So, this 5 is a relative time, like I was saying, it is 5 from the time that we are currently processing. So, a value of B05 is scheduled, that is one transaction, and similarly C110 is another transaction. Two new transactions enter the event queue. Then what happens? 5 nanoseconds later the transaction expires, right, on B, that is the earlier transaction. So, this expires, and as a result there is an event that is created on B. So, this is the only other transaction that is remaining. It would be expiring at time 25, and the value of C this time does change, and as a result an event is created on C. So, that is how that simulation waveform at an elementary level goes. Is that clear? The interplay between the transactions and the events. Transactions are created when some event occurs on a signal that is on the right hand side of an assignment statement. It is a possible change in value. We do not yet know whether it will actually lead to a change in value or not. You could argue from this example that there was that first transaction that did not even result in an event, because it did not change the value of C. So, why did we even bother to create the transaction? At the time that we posted the transaction, did we know or not that right. But in general, you post a new transaction, and at that time it seems as though its value is the same as the current value. Should you post the transaction or not?
Yes, you should.
Yeah, why?
An entry has to be made, right, for every transaction. So
I mean, before
Does it help us to post a transaction on a waveform when that value is the same as what is currently there?
yes, it can change in between and back again.
Yeah, in general I need to be careful about how I need. So, this is one example. It is not clear from this example whether it was worth it or not, but let us see other examples related to the correct handling of inertial delays, which did not necessarily come up right here. But this waveform is clear. This example is clear, hopefully. Yeah.
But also, if there is a glitch in A,
Yeah.
it will go unnoticed, or
We will handle the glitch situation right here. Yeah. That glitch has not occurred in this example as of now. So, this is sort of the simplest waveform you can think of. But this still illustrates the difference between an event and a transaction. That is important. Hopefully, we understand that all transactions do not necessarily result in an event. Okay. Although all events are necessarily created because of transactions that we post into the simulator. So,
What
yeah.
exactly is an event? We say that an event was created.
Yeah, event like we said is occurring when the value is changing on a signal. That is the simple definition. As this is a simulation specific meaning, of course, but that is what an event is.
So it might be possible that when a transaction expires, there are two variables, one of which is having its value changed.
Yeah.
One of the other one is constant. So in that case, also an event would be created.
When a transaction expires, two different assignments are sensitive to that same signal. Right.
So a transaction expires, one signal due to one variable, its value changes. The other variable, its value remains constant.
Right.
So an event would be created.
So, you are saying that a transaction is created, well, a transaction is posted first, okay. Later on it leads to an event being created. As a result of that event, maybe two other transactions, so maybe let me say call it a transaction on A, event is created on A. As a result of it, some transaction is created on B, is posted. Both the transactions are posted as of now, and some other transaction is posted on C, where this is our time. Both of these need not result in events on B and C. That is all right. The event has occurred on A because its value changed. Now, at that time we will see that as of now we are actually inserting all the transactions into the event queue, and if it turns out that the value that we had posted is the same as the current value, then there is no event. That happened in B, then there would be no event on B. If the value of C changed here, then there is an event here, maybe we say that there is no event on B. That is all right. But the way it is processed hopefully is clear, that at any point in time we maintain a bunch of such transactions that we had here. That is our event queue, and we simply pick up for processing the earliest transaction that is scheduled for processing, right. So, but of course, we have to handle the spikes or pulses in an appropriate way. Particularly, we already understand how that inertial delay works. The way we are processing the transactions and events has to be consistent in a way that we are able to handle inertial delay. We are also able to handle transport delay. But the underlying mechanism for handling both of these is the same. It is just transactions and events, but the way we are interpreting them would be different. Okay, so here is a statement that says A takes the value of 1 after 10 and 0 after 15, resulting in a waveform like this. It goes up at 10, right, that is 10, and at 15 it goes down. That is my waveform specification. The commas could be given to essentially specify a waveform on a particular signal. I gave 2 values here, you could give any number of values and any number of clauses could be introduced there, effectively leading to a very complex specification of a waveform as part of a single signal assignment statement. But by definition, that kind of a waveform specification refers to a transport delay. Inertial delay, remember, means that if you have a bunch of values being scheduled, the last one is what is picked up, the older ones would be thrown out. You can't specify a waveform if you are constrained by inertial delay. So, if you are specifying a waveform, it means that even if you did not write transport, it is actually treated as transport delay, otherwise an entire waveform would not appear. Okay. The other one, though, I have B takes not A after 8, this is a normal inertial delay specification. But you see the way this example is designed is such that this propagation delay is more than the width of that spike there. So, the issue that we had referred to with respect to inertial delay and how it is handled should be correctly handled now. So, at least this is a test case that should exercise that. Okay. How do we go about doing it? We have 2 transactions at time 0, we have initialized the values to 0. Even if you did not initialize it, the default value for the bit data type is 0. So, we have zeros on both A and B at time 0. Then I have one transaction A equals 1 being scheduled at 10 and another transaction A equals 0 being scheduled at 15. Right. So, both of these are entered here to be processed at different times. That is how we would handle transport delays, but as of now it is just a specification, and these I have these 2 transactions being entered into the queue, and I have one other transaction on B because I have not A being evaluated at time 0. At time 0 all the statements are evaluated. So, not A is evaluated. So, value of 1 is being scheduled on to B at time 8, right. So, 8 nanoseconds from time 0. So, that is 8. So, that is my event queue as of now. These are the 3 transactions that are there. That is the first transaction that is picked up for processing. So, that results in a transaction expiring at 8 and an event being created on B at time 8. Then what should happen? After that, I have the other 2 transactions remaining in my queue still. So, A110 is the next transaction that would expire. Every time an event is created, we have to look at our statements to find out which subset of the statements may need to be evaluated, right, and possibly transactions might be posted on them. So, because A changed and I have A occurring on the RHS of that statement, I should have a new computation and possibly a new transaction being created. Okay. So, I have a B08, that is because the new value of A is 1, a value of 0 is computed for B, and that is my new transaction B08. Okay, it will be processed whenever its time comes. So, since our current time is 10, the scheduled time for its processing is at 18. But what has happened is, in the meantime, before we could reach 18, the value of A has actually changed back to. So, this is the transaction 15 that expires first, right. That B's value that was scheduled at 18 does not expire, right. This one expires first. This is an interesting situation. What should happen here? That transaction on B is still there, it is pending to be processed, but the older transaction on A expired and a new event is created, which would lead to what? Which would lead to that statement being evaluated again. So, B08 was there, but now a new transaction is sought to be entered into the event queue, right. Here is a situation that we need to resolve in some way, because a value of 0 is scheduled for the future, but the current value of the input requires us to schedule something else into the future, that is further away. This 18 is further away from the 08 because we are at 15 now, right. So, there is something that is scheduled at 18, that is this one, but this one would be scheduled for 23, 8 from here. But this is a conflict and the inertial delay seeks to resolve this conflict. In what way should we resolve it? We will just cancel the old transaction. That way that spike does not get propagated to the output. Okay, so, we will say that this transaction that was there is actually cancelled and the B18 is what is still retained. That 18 remains in the queue. So, that is scheduled here at 23 and in fact, the value of B was already 1. Remember, it never went down because the earlier transaction was cancelled, right. So, we have 23 when this transaction expires, in fact, the value is already what it is, it does not result in an event being created. Neither the earlier event was created as a result of A going up, nor is the new event created as a result of A going down. This is the mechanism the simulator uses to suppress a spike. So, that essentially this 5 nanosecond pulse on A is considered the equivalent of a spike because it is small compared to the propagation delay of that gate at which it is the input. So, that is the simple mechanism the simulator uses to handle inertial delay, which is that if a new value is scheduled on a signal for which a transaction is already posted in the event queue, then we just cancel the old transaction and we enter the new transaction. Any questions on how this is handled? This is a simple and elegant way to handle the inertial delay, certainly. What if I had B equals transport? So, the earlier delay was an inertial delay and we know how to deal with that. Let us quickly go through this waveform. This is no different in the earlier stages. Actually, for A nothing changes, right? The processing of A is the same, it is the same statement. So, I have this transaction being scheduled, both of these transactions being scheduled onto A at time 0. B18 is scheduled for time 8, that is the same as earlier. At time 8, that transaction expires, right, the transaction for B expired first and the value of B is changed. So, I have an event being created on B. Let us move on. There is a transaction expiring on A at time 10 and an event is created at time 10. Okay. Now, because an event is created on signal A at time 10, what happens is that statement gets triggered because of the event. So, that statement is triggered and a new transaction B08 is scheduled 8 units of time for 8 nanoseconds from 10, which is scheduled to be processed at 18. Okay, we move on. So, I have 15. So, at time 15 I have the other event occurring on A and because of that event I would have this statement being executed again, which means that my new transaction would again be processed just as earlier, but this time what we say that is that we will retain the old transaction, we will not cancel the old transaction. Through this simple mechanism I will just permit the old transaction to be processed at the time that it was scheduled, which was 18, right. So, at time 18 we pick up B08 for processing and the value of B changes, event is created on B. Then at time 23, which is as a result of this, right, as a result of that 015 transaction, I have the new event being created on B. So, the difference was that earlier we cancelled the old transaction, we processed the new transaction, but the new transaction did not result in a change in the value of A because the value was the same. Here we just retained the old transaction, as a result of that there were two changes, two events that occurred on B. It is a simple mechanism to handle inertial versus transport delay. So, the mechanism is almost exactly the same. The way the events and the transactions are processed, they are common, but depending on whether the signal that is being assigned to is an inertial delay assignment or whether it is a transport delay assignment, we would make that simple change in the way it is processed in the signal queue. So, when the new transaction is posted, in the inertial case we will first look at the queue to find whether there is a pending event already on that signal. If it is there, then we cancel the pending event. In the transport delay case, we do not bother what is there, we just go ahead and post the new value anyway. That is it. That is the very simple way to discriminate between the two kinds of delay models. Okay. So, what you see on the output waveform is very different, but the way it is handled is just through a simple change of semantics. Of course, at the end, the final transaction that is processed is this one at 23. I have that event being generated, and that is the last transaction for this example. But this should give you an idea of how the simulator works. It is like an infinite loop in which the status of that event queue continues to change depending on what events are occurring. Okay. So, the moment an event occurs, maybe it triggers a bunch of statements. Each of those statements that event would sensitize possibly, those are all executed, and as a result of the execution, new transactions may be posted at different times in the future, depending on what those after clauses were, whether it is 10 or 15 or 8 and so on. Then, so we just modify the status of the event queue. We pick up one transaction to process from the event queue. That leads to possibly a bunch of different signal assignment statements being evaluated. As a result of that, a bunch of new transactions would be created. All of them are again put back into the event queue for processing. And what would the final step be? Well, the final step would be that you pick up the event, you process all of them. There may be multiple events that are expiring at our current time, right. So, after that all you have to do is you just forward time to the next scheduled event.
So,
yeah.
two transactions are simultaneously scheduled, like both of them are scheduled after 8 nanoseconds or something. That how will it organize in the event queue?
Let us see, I have two transactions being simultaneously scheduled. How will that come about? Let us see what kind of statements would lead to two transactions being scheduled at the same time.
B is equal to not A after 10 nanoseconds.
Okay.
After 10 nanoseconds, and C is equal to not A after 10 nanoseconds.
C equals not A after 10 nanoseconds. Fine. So, this time goes from left to right, and at some time I have A changing, let us say at 0 time. The value of A was, let us say I made it from 0 to 1. Okay. And as a result of that, 10 nanoseconds later, I have those two transactions B being, so let us say A changed to 1. So, I have B being 0, 10 and C being 0, 10. Right. So, both of these are there, these two transactions are there and they have to be processed. The order is not very important. Well, from the correctness point of view, the order is okay. You could pick up this one first for processing. A more detailed treatment of this situation where time is not changing, but maybe multiple iterations might happen, we will get to. But as of now, you can just assume that we will pick up one transaction, does not matter which one, and process it, and then we will move to the next one and process it. For now, this is what would happen. Yeah.
These are two events or a single event at time?
These are different. There is an event on B, there is another event on C. The event is associated with a signal. So, we say an event has occurred on signal B and another event has occurred or has not occurred on signal C. So, two events are created, two transactions are posted. In the general case, both of them might result in events, so that is what might happen here.
But in a different case, suppose the event on B affects C.
But okay, why do not we get to that later? I think you are referring to a situation where the event on B, let us say you have not A, you could have a statement that says B equals A and C or something like that, and both of them are scheduled. It is possible that multiple transactions may need to be scheduled onto the same signal without time moving forward. That is also possible, does not introduce any inconsistency, but we will look at that. A simple application of those delays, of course, is a kind of statements where you are generating clocks. There would be a very simple way to just say A takes the value of not A after a delay. do you see that it creates an infinite sequence of events, right. So, as a result of that statement executed at time 0, we would schedule a transaction at time 10. That transaction expires at time 10 and it creates an event on A. There is nothing that is stopping us from including the same signal on both the left hand side and right hand side, it is okay, it is consistent. So, since the value of A changed, now that statement would be executed again, because A also occurs on the right hand side. So, now because I am inverting the value of a new value which is 1 would be scheduled. As a result of this, I have a new value being scheduled. As a result of this event, I have a new value being scheduled. So, this goes on forever, and that in fact would be a standard way of creating clock kind of statement. This is a simple clock, but you can, by varying these after clauses, you can have multiple after clauses. Remember, you can have clocks of different kinds where the on and off portions need not be equal. Right. Okay. That brings us to one final aspect which is called delta delays. It handles this situation that was pointed out, where multiple triggerings of statements might happen without time being forwarded. Right. So, let us say I have a bunch of these 3 statements, I have B, C, D being assigned. So, these are concurrent signal assignment statements. Let us assume that, well, B, C are signals internal to the architecture, and I have statements like this which are 0 delay signal assignments, all are 0 delay signal assignments. But what is interesting about this sequence is that you see, as a result of A changing, I have that statement being triggered, but that other statement C is being triggered on clock changing, which is fine. Remember, if any signal changes in that RHS expression, then we should be re-evaluating it. So, C may be triggered not merely because that input clock is changing, but also because one of the internal signals B is changing, and in fact time might not have forwarded between the 2 triggerings. So, that is why it is in some ways an interesting case that needs to be separately looked at. So, let us say at a particular time I have these values on the inputs, both are input ports, A and clock are input ports. A is taking the value of 0, and let us say the value of clock was already 1 at that time. Because the value of A is changing, I have this statement being triggered. So, a value of 1 is being scheduled on to B, a transaction is posted, but that transaction is posted with a 0 delay, right, because I have to process that statement without time forwarding, that is the specification, and I have to observe that. Whether that is reality or not is a different matter, it is a practical reality or not. In practice, nothing happens in 0 time, but still 0 delay has important modeling related advantages. It is worth writing 0 delay signal assignment statements for understanding functionality, but also more important, like we had said earlier, these kind of statements can be input to a synthesis tool at a time when we have not decided the details of the circuit.
So clock is a keyword of the language.
No, clock is an input port of this entity which is not shown here. Yeah. Fine. So, I have to post a transaction B equals 1, right. I have a B value of 1, but delay 0 has to be somehow inserted into my event queue for processing. Okay. So, actually it is no different from the standard, the general algorithm that we had looked earlier, but of course, because this transaction has a 0 delay, this is the one that would be picked up when I conceptually forward my time. The time is actually not forwarding, but we forward it through a mechanism called a delta delay. These are the iterations that we go through in the simulator, and internally the event queue is being processed, but the time is actually not forwarding. Okay. But we are of course guaranteed that this transaction will be processed immediately, right, because it is scheduled for immediate processing, even though all the other transactions are there in the event queue. This is the transaction that will be actually converted into an event, let us say. Because the time has not forwarded, we divide the time into what are called delta cycles. So, I have my time, let us say, is 10 nanoseconds. at 10 nanoseconds all of these A changed, and so these inputs changed at 10 nanoseconds. As a result of this, what happens is that a sequence of triggerings happen, but the immediate consequence of A changing is just that one statement is evaluated. All the statements are not evaluated because they are not sensitive to A. What I meant here is that the clock is not changing, the value of clock is stable at 1, only A changed. Okay. As a result of A changing, only B can change, others cannot change, that is our algorithm of the simulator. So, what we will do is we schedule that transaction, right, we post that transaction at what is called the next delta cycle of a simulator. This is a simulator's internal concept, that is the way they treat this. So, delta means that the time is still 10 nanoseconds, right, the time has not changed, but we just move to what is called the next delta cycle. So, in the first delta cycle the values of, so A changed at this, A and clock, both of these changed. This resulted in some processing. So, it is resulted in that first statement getting evaluated and that transaction being posted for B at the first delta. So, this is the first delta, but still this the first delta is still earlier than all the other transactions that are pending on the queue. So, we just pick up the transaction that we just entered, that is the transaction that would be picked up for processing. So, we process B10, then what happens? Because of that the value of B changes. So, because the value of B changes, these other two statements assigning to C and D will actually be evaluated, right. Now, it will be evaluated without time being forwarded. So, this is processed, right, but in the process what happens is two more transactions will be entered here. One is that C, I have a value of 0, what is the time? Still 0 is the relative time from now. For D the value is 1, but the time is the same thing. Both of these events would now get created and inserted into the event queue in the normal way that even the event queue anyway works. Then what should happen? So, then we say that we are done with the first delta, we move to the next delta. So, that is my delta 2. So, I move to the next delta. So, actually the way I wrote this up, you can think of maybe this as the first delta, this is the second delta, and that is my third delta, right. So, at that third delta these are taken up, both of those transactions are taken up for processing. So, they result in new events. So, new events may be created on C and D, and then what happens? As it happens that assignment to D actually has C on the right hand side. Now, since an event was created on C, that may result in a new transaction. So, the others are okay, B is sensitive to A, that is fine, C is sensitive to clock and B, that is fine, but because C changed, now I may need to change D, and therefore, what happens is a value of 0, new value of 0 is posted on to D with the time being 0, still all of these are 0 delay. So, that is my new transaction that would be posted here for processing in my delta 4. So, that may lead to a new event being created on D, that should lead to a stable situation as far as the time t equals 10 nanoseconds is concerned. No more events to be processed, no more transactions to be created or events to be created at time 10 nanoseconds. After that we move to, so since we are done with t equals 10, we now look at the event queue to see what other events might be there and picked up the next one, maybe the next event is at 15 nanosecond perhaps. But this is the sequence of delta delays that is important from the point of view of handling the 0 delayed transaction. So, point is the same assignment statement might be triggered multiple times. You see that there were multiple transactions being posted onto D without time changing, and it has happened in a normal way. If it happens that multiple transactions are inserted, you process all of them. As a result of processing each of those transactions, another bunch of transactions may need to be scheduled, and they are scheduled into the next delta cycle. You can have any number of delta cycles, but the treatment of the simulator would be the same as what we already saw. Yeah.
So if we if we make the transaction on D, transition on D,
Right.
if we put transport delay, then what would happen? Because this is delta function, delta delay, right? So
If it was a transport delay instead of inertial delay, so this statement, the assignment to D was a transport delay. So it is possible that as a result of these sequence of events that are created without time being changed, you end up in a situation where the same signal may have values that go up and down without time progressing. It is possible, right? If there was another event, let us say, was scheduled on to D in a future delta, it is possible that you go up and you come back without time progressing. The mechanism for distinguishing between inertial and transport delays is still the same. So, if they happened in sequence, then they show up like this. It may not be visible in the waveform that you see. These are internal states really, this goes up and down. Simulator might give you a mechanism for expanding the view at a particular time to observe deltas. By default, the deltas are not visible in the normal simulation. This is just there to illustrate and for us to understand what is going on internally. But the treatment is no different than the standard transport delay, which is if it happens, maybe we insert multiple transactions into the event queue if it is transport. The way this happened here, it does not matter, even if it was inertial delay, it would still the spikes would show up, but only in the deltas, which are meaningless anyway. This is a simulation concept, this is not the real waveform. Yeah.
So what if there is a loop back?
The bunch of statements that you write here could have a cycle in terms of dependency, right. I can have A depends on B, B depends on C, C depends on A. This is considered a correct VHDL statement, there is nothing wrong in it. In fact, it could represent correct hardware also. We said that the standard mechanism for creating a clock was A takes the value of not A after 10 nanosecond. What if you had written A takes the value of not A? Is this correct language? Syntactically, is it correct VHDL? It is correct, there is nothing that is preventing us from writing like this, so the compiler would go through. We will generate a design that at simulation time, what happens? At time 0, what happens?
Spike and internal state will change, but the output is
Internal state will change, how many times? Think in terms of the delta cycle. Every time you have a 0 delay, you have to think in terms, the processing would be in terms of the delta cycles. What happens? At time 0, at first delta, let us say we initialized everything. In the next delta, we are scheduling that event A. So, let us say 1 is scheduled at time 0. Okay. In the next delta, what happens? So, A 0 is scheduled. How many deltas do we go through? An infinite number of times. Simulators normally will warn you that the way you have written your statement, simulation will not even proceed. Right. So, that is what is there. So, it is legally correct, you can check it out if you want to, but there may be uses. Creating statement like this is the perfect use of introducing a cycle. Since you can do it in one statement, you could also do introduce that cycle through a sequence of statements and it would be okay, fine. But it is fine. So, just like in sequential design, you can have output of one stage feeding back to the input of another stage. So, the cycles are okay, they are permitted. We should understand, of course, what we have written. Hopefully, those cycles should not be combinational cycles, right. That is when there may be some issue.
One more question. If two signals, so it's a multi-input gate like NAND or some other function, and both the signals are reaching at the same time, different values will come in, and it's a race kind of condition that if I choose first one as the delta, then my output will be different. If I choose the other one as my first delta, then the output will be different, depending on I choose.
So, there is some such feedback from output to the input.
It will be coming from the previous portion of the circuit. but both the signals have arrived at the same time, exactly same time. So how does simulator choose to?
At the heart of the simulator's algorithm, there is no intelligent resolution that is being made. The algorithm is indeed what we just said, and when there are a bunch of transactions expiring at a particular time, the simulator will pick them up in an order that is unspecified. The language does not insist that you pick up in this order or the other order.
It's an implementation.
It is left to the implementation of the simulator, and in fact the designer has to be careful to make sure that the expected functionality does not depend on the order in which the simulator is going to pick up the events for processing.
So, like these are posted for, but when are these processed? That processing should also happen at 0 time.
Yeah, so all the events, all the transactions that are posted with 0 time would be picked up for the next delta. All of them would be taken up for processing.
So it doesn't matter how many deltas are there. And
You do not know how many deltas are going to be there. See, the processing of events at a particular delta may create 7 new events, all of them are processed for the are posted for the next delta. So, when it comes to next delta, in some order I am going to process all of them, maybe it will result in 5 new events being created. Those 5 new events again may lead to maybe 8 new transactions, all of them are posted for the next delta. So, it is only one delta at a time that we are processing. We do not post something for 3 deltas from now, because it is a 0 time, we are only posting it for the next delta, but we do not know when we are posting it how many times I need to iterate, because that is that depends on the functionality.
graphically we will see the final values, we will not see these transactions or
Graphic, so the default waveform will only give us the final values, but I think simulators may give you an option to also look at the delta transitions at a particular time. You can say that show me the expand the deltas, and they might, I think, yeah. But the standard waveform will not show it to you.